After some time, you get a 1 gigabyte provenance chain for this small file. But some events are not really interesting, not important. Maybe you opened the file and changed a comma or added a dot, period or something, and that's probably not very interesting. So if you want to remove certain entries from the provenance chain in a systematic way to save space, what do? Recall that we cannot remove entries from the provenance chain because that breaks integrity. So the original scheme doesn't allow us to summarize, but if we change the scheme a little bit, we can do that. So instead of having one checksums per entry, we can have multiple checksums per entry. For example, take say this entry, the third entry from the left. Here, suppose we have add 2 checksums here. One checksum is calculated by taking the checksums from the previous entry and the current entry and then signing it and so on. And the other checksum is calculated by following this red line to this previous entry 1 entries away, and then using that checksum to compute the new one. So what will happen is that now we have provided a way to skip over this second entry to go from the first entry directly to the third one. So now we can remove these entries, but still be able to prove that the third entry is chronologically after the first entry. So it might sound contrary to our original goals. Originally we said we don't want people to remove, but here we are providing a way to remove. So what actually we have done here is to provide a way to systematically remove things from the history. So now an auditor can audit this document, verify integrity, but he will also know that there are some existing holes in the document and where the holes are. Okay. So let's go back to the place where I defined plausibility with all this branching. So what we said there is that using our scheme, we can provide one type of guarantee. We can, if I give you a document and a provenance chain, you can audit it fine. You can audit it and say, look, say that nothing has been changed in the provenance chain. But you can't say that this is exactly what happened. Rather, we can only say that this is a plausible provenance chain. This is something that could have happened. Something could have brought the document from its original state to its final state. So we cannot say this is what happened for sure. We just say this is something that could have happened, but there might be cases where this is important. So an easy attack by an adversary would be like this. The adversary just removes all the provenance chain of a document. Maybe there's a famous poem, and then the adversary removes the provenance chain showing the poem was written by Shakespeare, and then adds his fake provenance chain showing it was written by him. He adds a few signatures from a few friends. So the provenance chain is now plausible, but it's not real. It's also not tampered because he included his signatures from his friends. So how can we provide stronger guarantees? We can provide stronger guarantees by entangling the provenance chains of related document. How do we do that? Here's an example. Suppose we have these 2 documents, the blue document and the green document. And each of them have these 2 provenance chains, the blue chain and the green chain. Now, an adversary can do this. Adversary can maybe remove this entry and the last entry and the previous entry and add his fake entries here at the end of the chain. So the history is plausible because he computed these new fake entries, but it's not real. However, if we do this, we do a variation of the spiral provenance chain I just described earlier. If we do a variation of that, so rather than entangling a document with itself, we entangle the document with other documents. So here, suppose that in this green entry, we include 2 checksums. One is computed from the previous green entry. The other is computed from the last blue entry. So now we have made the green chain dependent on the blue chain. So now if you tamper with these 2 entries, you will not detect that when you are verifying the integrity of this one, but you will catch that right away when you are verifying the integrity of the green chain, because this fake entry will affect the checksum of this one. It will not match the checksum you have stored here. So in that way, we can entangle a group of documents and have stronger provenance guarantees. Now we can say for sure that this is what happened, because if you create a fake chain, then all the related documents would not match. Their provenance chains and their checksums would not match. And how do we say which document is related? Well, maybe all the babies born on the same date, we can entangle their birth records, birth certificates. Maybe you visited a doctor and all the people who visited the doctor in that particular day, you can entangle their medical records of those people. So now implementation. All this theory is fine, and we have used some existing techniques to provide these guarantees. Okay, that's fine. But is it practical? Can we use it in a file system? So we wanted to check whether we can get good performance numbers, and we wanted to do that in a file system. And there are different layers where you can add that. You can add that to the kernel layer. That will be transparent to existing apps. You don't have to change existing apps. You can also add to the file system layer, and finally you can add that to the application layer. So only the particular application that needs provenance would record them. So we chose the last approach. We created an application layer library which we called SPRO, and the goal of SPRO is to capture file system I/O activities and record that in a secure manner. So this is how SPRO works. SPRO captures all the file system calls. So whenever you open a file, do a write, a read, something like that, all that goes through SPRO, and SPRO now creates appropriate provenance entries and add them to the provenance chain, and then passes off the file system call to the file system directly. And these provenance chain are stored as XML formatted files on the same storage system, or it can be also stored as database tuples. And one of the goals we had is to make it as portable and as easy to deploy as possible. So we provide a wrapper for all the file system I/O in the standard IO.h library. And to have secure provenance in any application, you just use our header files and then recompile, and also change the file system calls to use our file system calls. So I'll just skip this slide to go on to the experiments. So the goal of our experiment is to measure the runtime overhead. So someone from the industry once told me that if any fancy new scheme, security scheme, causes your system to run more than 3% slower, more than 3% overheads, the people will not use it in practice. So we wanted to show or check how much overhead our system would have if you have secure provenance. So we ran a number of different benchmarks, and here's our experimental settings. We used 1024-bit DSS signatures and SHA-1 and so on, and we used two types of benchmarks. The first one is the Postmark Benchmark, which is a benchmark for small files. The other one is what we call the hybrid workload benchmark, which is a benchmark with realistic file systems and also realistic file system workloads from file system literature. Okay. We also used two modes for storing the chain. In one mode, the provenance chains were stored directly on the disk. In the other mode, they were first buffered in a RAM disk and periodically flushed to the disk. So first, let's see the Postmark numbers. Postmark, as I said, is a benchmark for small files, and we created, we ran Postmark with 20,000 small files, really small, 8 kilobytes to 64 kilobytes, and we varied the read-write bias, that is the percentage of read transactions. And on the left side of the screen, you'll see the case where all the transactions are writes. And on the right side, you'll see the case where all the transactions are reads, no writes, everything is reads. And we measured the runtime overhead. So at the bottom of the screen, at the top curve, you see the overheads for config disk mode, where we stored the provenance chain on disk. And the bottom, you see the case where we stored the where we buffered the chains first in a RAM disk and periodically flushed them. So here you see that at 100% write load, when all we have is writes, the overhead for config disk is around 27%, and with the RAM disk optimization, we go down to 12%. As we increase the reads and reduce the writes, the overhead goes down, and here the area of interest is actually here, 80 to 100% reads,